Hi, this lesson is about the definite integral and the indefinite integral. The difference between the definite integral and the indefinite integral are the limits. The definite integral has a lower limit and an upper limit, and the indefinite integral does not. So the way we evaluate them, there will be some differences, but also some similarities. So first we're going to talk about how to evaluate a definite integral. And in order to find the value of a definite integral, we're going to use the fundamental theorem of calculus, which I'm going to abbreviate as FTC just for convenience. The fundamental theorem of calculus is in two parts. I'm going to present part 2 first and then part 1. Part 1 and part 2 can be called the opposite way in different textbooks. So sometimes part 2 is part 1. It depends on the author, and part 1 is part 2. So I'm starting with part 2. What's important is what the theorem says. So the theorem is here in this pink box. It says, if f of x is continuous on a closed interval, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F of x is the antiderivative of little f of x. And since it is an antiderivative, then this must be true, that capital F prime of x must equal the integrand little f of x. So that's always a good thing to check until you're really good at integrating. So this is a more efficient way of evaluating the definite integral, other than the Riemann sum, which we know has quite a bit of algebraic work to do in it. So this one's more straightforward. So let's do an example. And if you recall from previous lessons, I did this first example with the Riemann sum. So we want to integrate x squared from 0 to 1 with respect to x. So that's why we have a dx there. So remember, the antiderivative of x squared, you have to apply the anti-power rule, which means you add 1 to the exponent and then you multiply by the reciprocal. So we have 1/3 x cubed, and then we have to evaluate that from 0 to 1. Notice that after I've integrated, you no longer write the integral symbol, and your limits get written on the right. We put this vertical bar to the right of your antiderivative, and then you put your limits to the right in the same order, the lower limit 0 at the bottom and the upper limit 1 at the top. So now is when we're going to actually apply the theorem, actually do this work. Plug in the upper limit and then subtract out when you plug in the lower limit. So that's what I did here. So I have 1/3 times, and then I plug in the 1, so that's 1 cubed, plug in the 0, minus 0 cubed, and so the value of the definite integral is 1/3. Remember that the definite integral represents the area under a curve. So what this one represents is that the area of from 0 to 1 of x cubed, that area computation is 1/3. All right, so let's do another example. This next example has some trigonometry. So part B says to evaluate the integral from 0 to pi over 2 of 4 cosine of theta d theta. So I'm going to factor out the 4. We can do that because of one of the integral properties. You can put the 4 in front of the integral. And then all we have to do is worry about integrating or finding the antiderivative of cosine. Well, the antiderivative of cosine is sine, so we have to evaluate 4 sine of theta from 0 to pi over 2. So this is the part where we're applying the fundamental theorem of calculus, part 2. You plug in your upper limit first, and then you subtract, plugging in the lower limit. So the sine of pi over 2 is 1, so it's 4 times 1, and the sine of 0 is 0, so your final answer is just 4. Okay, let's move on to part C. Part C requires that you do some algebra before you actually take the antiderivative. So I've given you an integrand that's a product. I have 3t minus 1 times t plus 2. Now we don't have an anti-product rule, but we do have the anti-power rule. So the in order to use anti-power rule, we have to expand or FOIL this integrand so that we have separate terms like you see in this line. So when you FOIL your integrand, you get 3t squared plus 5t minus 2. Now we're ready to take the antiderivative, and that's our third line. So you take you apply the anti-power rule to the first two terms. So for the first one, you add 1 to the exponent and multiply by a third, and then the 3 in front and the 1/3 cancel. So that's why your first term is just t cubed. You do the same thing with the second term. You add 1 to the exponent, so you get t squared, and then multiply by the reciprocal of 2, which is a half. So we have a coefficient of 5/2. And the antiderivative of a constant is just the constant with the variable attached to it. So remember, that means that f of x is t cubed plus 5/2 t squared minus 2t. And if you weren't sure if you took the antiderivative property, then f prime of x should equal what you see right in here, and it does. This is 3t squared plus 5t minus 2. So you should be able to go back and forth easily. And now we're ready to evaluate the antiderivative at the two limits. So that's indicated in this line. And in the next line, we plug in the upper limit first, the 2, and then the lower limit. And remember, you have to subtract when you plug in the lower limit. So I put the minus sign there, and then parentheses to show that I have to distribute that negative. And when you work this all out, you end up with a value of 21/2. And so again, that represents the area under the curve of 3t minus 1 times t plus 2 from -1 to 2. Okay. D is kind of similar to C in that you have to do some simplifying before you take the antiderivative. So the original problem is a quotient. We do not have an anti-quotient rule, just like we don't have an anti-power rule. So in order to use the we don't have an anti-product rule, as I mentioned in the previous example. So in order to use the anti-power rule, each of these terms have to be separated into individual terms. So each one will get divided by the square root of a half, which is w to the 1/2. And remember that your rules for exponents is that if you have an exponential expression in the numerator and another one in the denominator with the same base, that you can combine them by subtracting the exponents. And that's exactly what I did in this line. So from the first line to the second line, I just subtracted the exponents for the first two terms. And for the last term, well, I wrote it instead of 1/w to the 1/2, I brought the w up to the numerator, and therefore the sign of the exponent changed. So now those three terms in the integrand are ready to be taken the antiderivative of, so that I can apply the anti-power rule to it. So the antiderivative is here. As soon as you're taking the antiderivative, you no longer write your integral symbol. You notice it's not here, and your limits get written on the right. So that's why it's here on the right. Okay, so we add 1 to the exponent, and we multiply by the reciprocal of the exponent. So 1 added to 3/2 gives me 5/2, and then multiply by 2/5. And then add 1 to a half, we get 3/2, and then multiply by 2/3. Add 1 to -1/2, and that gives me a half, and then multiply by the reciprocal, which is 2. Then you want to multiply all of those coefficients. So I get this line, 6/5, and I'm also plugging in my limits. So I have 6/5 square root of 4 to the 5th power minus 2/3 square root of 4 to the 3rd power plus 2 square root of 4. And then again, you have to subtract when you plug in your lower limit. So all of this is in parentheses. And there you plug in 1. So notice that I also, in this same line, I rewrote my exponential expressions as radicals. So the rule is that if you have a rational number as an exponent, it can be rewritten as a radical where the denominator of the exponent is the root and the rest of it goes on the inside. But it also means the same as this that I'm writing down now, which is take the nth root and then raise it to the mth power. And I'm actually applying this here because it just makes the math a little bit easier for me to do. So in the following line, I took the square root of 4 and 1 when I plugged it in, and that's what you get here. So I have 6/5, 2 to the 5th, minus 2/3, 2 to the 3rd, plus 2 times 2. And then here I also distributed the negative. This negative got distributed across. So that's what you see here. So minus 6/5 plus 2/3 minus 2. And then I'm ready to start combining numbers. Then I raised all of my 2 to the particular power. So here I did 2 to the 5th times 6. That's where I get 192 over 5. Then I did 2 to the 3rd times 2. That's when I get minus 16 over 3. And then plus 4 minus 6/5 plus 2/3 minus 2. In this next line, I combined the fractions with the denominator of 5 first. So I get 186 over 5. Then the two fractions with a denominator of 3 gave me minus 14 over 3. And then my two integers gave me just 2. Then here my LCD is 15. So the first term got multiplied by 3, the second one by 5, and the last one by 15. So when you combine those numbers in the numerator, you get a integral value of 518 over 15. All right, so here's another definite integral. We want to integrate from 1 over root 3 to root 3 of 2 over 1 plus x squared dx. So just like the previous examples, I factored out the coefficient, which is 2, and then I'm just left with the integral of 1 over 1 plus x squared. Well, hopefully you remember this. This is actually the derivative of tan inverse. So the antiderivative is 2 times tan inverse of x. And that has to get evaluated from 1 over root 3 to 3. So remember, plug in the upper limit first. So that's what we see here. So I have 2 times tan inverse of root 3 minus tan inverse of 1 over root 3. And now root 3 and 1 over root 3, that's a special triangle. It's a 30, 60, 90. So I'll just draw it here. So if this is 30 degrees and this is 60 and this is 90, that means that this is 1, this is root 3, and 2. So let's consider 30. Remember, tangent is opposite over adjacent. So the tangent of 30 is 1 over root 3. And if you look at it from the perspective of 60 degrees, opposite over adjacent, then that's root 3 over 1. So that's exactly what I have here. So the first one, tan inverse of root 3, that's 60 degrees. Now 60 degrees is the same as pi over 3. So that's why you see pi over 3 first. And the second one, tan inverse of 1 over root 3, well, that's 30 degrees. And 30 degrees is the same as pi over 6. So again, that's what I wrote on this line here. Then here I got a common denominator of 6. So I have 2 times 2 pi minus pi over 6. So 2 pi minus pi gives me pi over 6 times 2. But 2 and 6 cancel. They have a common factor of 2. So your final answer is just pi over 3. Okay, so make sure you remember your 30, 60, 90 triangles and your 45, 45 triangle. All right, so here's another one. We want to evaluate the integral from 1 to e squared of 3 over t dt. So just like the last example, I factored out the 3. And then you can see that the integrand that you're worried about is 1 over t. Well, 1 over t is the derivative of ln of t. So the antiderivative of 1 over t is ln of t multiplied by 3. Now we're ready to evaluate ln of t at these integrals. So that's what you see here. So I left the 3 in front of the expression. So I have 3 times ln of e squared minus ln of 1. Well, remember, natural log and e are inverse functions. So ln of e squared, well, that has a value of 2, and ln of 1 has a value of 0. So your final answer is just 6. Okay, so that's something that you need to remember from pre-calc. So just put here on the side that ln of e to the x is equal to x for any value of x, and ln of 1, or the log of any base of 1, is always equal to 0. Okay, so this one, similar work, but it'll be a little bit more visual because we're going to sketch the graph represented by this integral and then compute the area, and we're going to use the fundamental theorem of calculus. All right, so our integrand 1 minus x squared is a parabola with a vertex at 0, 1 that's facing downward because my leading coefficient is negative. So that's the graph that you see here. The curve 1 minus x squared is the one in black. The area represented by the integral is the one shaded in blue. So I have a negative area here because it's below the x-axis, and a positive area here because it's above the x-axis. Okay, so we need to see what the net area is. So to compute the area, I'm going to integrate from -2 to 1, 1 minus x squared. So we can go straight to just using anti-power rule. So that gives me x minus a third x cubed. Here we plug in our upper limit minus our lower limit. And so we get 1 minus a third plus 2 minus 8/3. When I combine the constants, 1 plus 2 is 3. Combine the fractions. Negative a third minus 8/3 is negative 9/3. But negative 9/3 is minus 3. So basically 3 minus 3 gives me a net area of 0. So what that means is that the area below the curve and the area above the curve is the same, except one is negative and one is positive because of the position of where that area is. So they cancel each other out. All right, so here are a few indefinite integrals. Indefinite integrals are less work because there are no limits for you to plug in. But what you have to remember is that when you are evaluating or integrating an indefinite integral, that you have to add a plus c or a constant to your answer. All right, so here's the first one, A. We have 3 secant squared of theta d theta. So first thing I did was factored out the 3. So I have 3 integral of secant squared theta d theta. Well, secant squared is the derivative of tangent. So the antiderivative, or the value of this indefinite integral, is 3 tangent of theta plus c. And again, your check would be, if you took the derivative of the answer, you should get back to your integrand. And it works. So it might help to look over all of your derivative rules from previous chapters so that when you're integrating, you recognize secant squared as something that you should know. Okay, so here's B. I have 2 e to the x plus 1 dx. And so we're integrating that. I'm going to separate this out into 2 separate integrals in the next line. So I have the 2 factored out. And so I'm integrating e to the x dx plus 1 dx. The antiderivative of e to the x is just itself, just like the derivative of e to the x is also e to the x. And the antiderivative of the constant 1 is x, so your answer is 2 e to the x plus your constant of integration. So don't forget that c. And they usually use capital C. So here's another one, part C. I have the integral of 5 over the square root of 1 minus t squared dt. So again, I'm factoring out the 5. So I have 5, the integral of 1 over the square root of 1, this is a typo, 1 minus t squared dt. 1 minus t squared dt, hopefully that rings a bell, because that is the derivative of arcsine or sine inverse. So your antiderivative is 5 sine inverse of t plus c. All right, so let's go to the top here. So here I want to integrate 3x plus 5. This is part D. 3x plus 5 over x squared dx. All right, so first I'm going to simplify this. Again, because I don't have an anti-quotient rule and this isn't something that I recognize as a derivative that I know, I'm going to divide each term by x squared. So that's what you see here. And then you simplify. So I have 3 over x plus 5 over x squared. All right, so now these are something I can work with. So again, I'm going to separate these out into two separate integrals and do a little bit of rewriting. So the first integral is 3 integral of 1 over x dx. And the next one is 5, so the coefficient goes in front. And I'm rewriting the 5 over x squared, so where the 5 is the coefficient of the integral, and rewrite the 1 over x squared as x to the negative 2, so that I can apply anti-parallel. All right, so 1 over x, that is the derivative of ln, so the antiderivative is ln of x. And notice that I put x inside of the absolute value symbol, and that's because the domain of the natural log function is all positive real numbers. So your x cannot be negative, it would be undefined. So we are forcing it to be positive by including that absolute value there. And then here, anti-parallel, add 1, which gives you x to the negative 1, and then multiply by the reciprocal, which is also negative 1. So your final answer is what you see here, 3 ln of the absolute value of x minus 5 over x plus c. Okay. Here's another, it's actually the last one. I have the integral of 2t squared minus 2 over t to the fourth minus 1 dt. All right, so this one again doesn't stand out as something that I know or recognize, but I can simplify this expression, so let's see if that helps. So both the numerator and the denominator can be factored. So in the numerator, I factored out a 2, leaving me with t squared minus 1, and the denominator, that was the difference of perfect squares, so that becomes t squared plus 1 times t squared minus 1. Once you do the factoring, you can see that the t squared minus 1s will cancel each other out, and you're left with a new integral. Here, I factored out the 2 in front of the integral symbol, so I have 2 integral of 1 over t squared plus 1. And again, this is one, hopefully that reminds you of something that you know. That is the derivative of tan inverse. So the antiderivative is what you see here, 2 tan inverse of t plus your constant c. Okay, so now you should be ready to try the homework for this section. Good luck.